We can start. I don't see all the usual faces, but hopefully some people will still come.
Okay.
Yeah. Please. Okay, we will speak slowly, so if somebody is late, they will not miss too much. So on the last lecture, we started discussing the topic of nonlinear sigma model. And the first step was introducing a Grassmann valued field, Grassmann valued. Grassmann valued field. Field just means a function of point. So the field was phi, which depends on r. It's a function of position in space that takes values from some Grassmann algebra, and it has either retarded or advanced index, and it also has a replica index I, which is a number from 1 up to n. N is the number of replicas. And we have a similar conjugate field, phi star, which is also retarded or advanced and has the same index. So this is the full collection of the fields, and I'm just now repeating what was last time, so no need to follow yet. So we introduced something which is called action, some functional S, which depends on these fields, and which by definition is minus I, integral over the whole space, phi dagger, and then an operator that is like the inverse green function. It's energy minus psi of t plus v of r plus our random potential. Sorry. It's also minus. And then we had omega over 2 lambda and I0 lambda here, and another phi field. This is the action. Lambda is a special matrix which is 1, 0, 0, minus 1 in this retarded advanced indices. Okay, so this is the action. Why do we need this action? There was a...
This is big 5 probably. Big 5 conjugate.
So far, they are all the same phis. What's the question? You mean this one is small, that one is big?
Yeah.
I'm not sure. Let this be also big. Yeah, so this whole thing was needed because we have a following expression for the green for the green function. Green function is represented as a Gaussian integral over these fields phi, and the action is what we have in the exponent of this Gaussian integral. So the green function, which is either retarded or advanced, at the energy which is epsilon either plus or minus omega over 2, and which depends on 2 points r and r prime, was equal to minus I integral over all these fields, phi star and phi. And then there was a special prefactor here, which is phi at point r either retarded or advanced, taken from the replica number 1, phi star either retarded or advanced at the point r prime at the replica number 1, then exponent of minus this action. So this integral almost defines the green function. The only thing to be done here is to take the replica limit, the limit n to 0. So last time I explained what this replica trick does. There was a z factor in front, 1 over z, and the limit n to 0 is needed to get rid of this factor. Just as a reminder, the partition function z is the same integral without any pre-exponent. It's just the integral of e minus s. Well, so this is where we ended last time. Are there any questions to this point?
So those are just definitions. We didn't connect this green function to the green function.
No. It is the original green function. We have shown that this green function is the inverse of this operator. Is the matrix element of the inverse of this object, which is by definition the green function.
Yes. Okay.
So we have a green function defined in a usual way as the inverse of energy minus Hamiltonian, and this is just a new representation of the same object.
Just so then we take from the first replica. In general, it doesn't really matter.
It doesn't matter. You can. They are all equivalent. You can take from.
From the same replica.
Yeah, you can even take a sum over all replicas here and then divide by n and then take the limit. That's the same thing. Okay, so the next step, which was not done last time, is the disorder average. We have here inside our action this letter V of R, which is a random potential, which describes scattering on random impurities, and we would like to average our green function with respect to disorder average. And this is exactly why we needed this replica trick, because now disorder in this expression for the green function, disorder enters only linearly inside the exponent. And we are going to average this green function over all realizations of V, which is a Gaussian distribution as usual, and averaging the exponential over a Gaussian distribution is a very easy task. So, with 2 fingers, yeah. There is an identity, which I will just write here. The identity is like this. Whenever you have an exponential of any random object which has a Gaussian distribution, the average of this exponential is the exponent of 1/2 of the average square of this object. if A is Gaussian. And actually also if the average A is 0. Actually, I will not prove this identity because I forgot how to prove it. But I know how to memorize it. That's very easy. You take this exponential and you write it as a series. 1
It follows from Wick.
plus A squared over 2 and so on. Then you average. You say 1. This linear term is 0. And the next term is A squared average over 2. Then you say, aha, this looks like this exponent, like the expansion of this exponent.
This way you can also prove it to any other.
Yeah, of course, it's an exact identity, and as was already mentioned, it can be proven using the Wick theorem, or you can just compute the Gaussian integral with the Gaussian distribution of A explicitly. Right. So we will apply this identity to average the exponent of S that we have here. And this is what will happen. So average exponent of minus S equals. Well, actually, let me do it differently. I will not average the whole exponent. Let me average just the part which contains V. Average exponent of minus S, and S contains minus I, so it's I times the integral over all positions sum over all replicas phi dagger I V of R phi and it's minus here. So I have an exponent and it has many terms here, 1, 2, 3, 4, 5. All other terms are constant. They are not average, they are not random. This is the only random term in the exponent, and since I have an exponent, a product, I can just average each term separately. So this is what I have to do, and I will apply this identity here. So I write exponent of, now it should be 1/2 the average square of this object. You see I have minus I here, so the square will have a minus 1/2, and then it will be a double integral dr prime, double sum over replicas, phi dagger I phi I. I will write it's the functions of R, phi dagger j of R prime, phi j of R prime, and this is the end of the board, but I guess I can do like this. Huh? So the average V squared, the only remaining part is the average of V of R prime. And this thing here, this average, is, as we discussed many times, is a delta function of R minus R prime divided by 2 pi nu tau. It's the same thing we had in the diagrammatic technique before when we did same thing with diagrams. So I just continue the same line of identities. So this is the exponent of minus 1/2. Since I have a delta function, I can remove one of the integrations. I have not the integral over 2 points, they become a single point. So the integral over a single point. Then I have this number, 2 pi mu tau. And then I have 4 fields, 1, 2, 3, 4, all taken at the same point. That's why I will not write this R or R prime anymore. They're all at the same point. It's just the double sum, I and j, phi dagger I, phi I, phi dagger j, phi j. And now I will introduce a special notation. It's a matrix now. Matrix M, Mij, the matrix element, by definition, is phi I, phi j dagger. It's just convenient. So I have an exponent of 1 over 4 pi mu tau integral over the whole space and then trace of this matrix squared. So if you take 2 such matrices, write the square. I can do it here just for your convenience. Trace of m squared means trace, well, trace is not probably required, means m, means m I j, m j I, yeah, the summation over both indices, which is phi I, phi dagger j, phi j, phi dagger I. And this is almost the same as here. The only difference is that this one starts with phi dagger I and this one ends with phi dagger I. So to convert this trace to this product, I need to swap the last term here and put it in the first place. And these objects are Grassmann numbers, they anti-commute. So when you do the swap, you take the last one and you pull it through 1, 2, 3 other fields. So you do change sign in the end. That's why this minus disappeared on that side. So this trace m squared is actually the original sum with an opposite sign. Okay. Is this clear? Good. So what do we have? We have, after we average over disorder, we have a new term in the exponent which contains 4 fields instead of 2. It's not a Gaussian integral anymore. We had a Gaussian integral over phi originally. Now we have a new term in the exponent with 4 fields phi, and actually this term corresponds to what we did before to this dashed line, which has 2 green functions at the end, so it's like phi dagger, phi dagger. It's like this object in a diagram with 4 phi fields.
We replace the problem which can in principle be calculated exactly with the problem which cannot.
Well, actually, yes. Well, you can calculate exactly for a given function v of r. Now after averaging, it's an easier problem because you don't have this ugly function, but it's harder because it's not Gaussian. So the next step, which was the number there, 4, yeah. Step number 5. We should do something with this. It's like an interaction term, but it's not a real interaction. It's just a correlator of two disorder potentials. So we will introduce a new field to decouple this interaction term. And this step has a name. It's called the Hubbard-Stratonovich transformation. So I will apply this transformation only to this exponent. I'm leaving for a moment behind all other terms in the action. We're just working with this exponential which contains 4 fields phi or 2 matrices M. So we start just from the same expression. Exponent of 1 over 4 pi nu tau integral over r trace of m squared. Actually this m, I forgot to say, it's also a function of position. Each field is taken at the same point in space. So inside this M matrix, I take 2 fields at the same point. So this matrix also depends on a single point. And this thing is integrated over the whole space. So I will do something strange to this exponential. I will first write this thing and then I will explain what happened. I will write an integral over something that is called q, and then exponent with the following content minus pi nu over 4 tau integral over the whole space trace q minus m over pi nu squared plus 1 over 2 tau integral over r trace q times m. The end. Oh, sorry. I completely misinterpreted everything. This trace. Integral over r divided by 4 pi nu tau trace of m squared. So what just happened? I had this exponent, and without any change, this exponent migrated to here. So what I did, I just took this exponent and I multiplied it with a q integral of this other exponent. I just had a number, I multiplied it with a different number. This number here, the q integral of this exponent, is just a Gaussian integral. And q is a matrix. Q is a matrix of the same size as m. It's just similar.
It should be true up to a numerical constant.
Yes, it's true up to a numerical constant, and this numerical constant, it's a Gaussian integral. Q is a matrix, it has many matrix elements, and this is a Gaussian integral, and this Gaussian integral equals pi nu over 4 tau, the coefficient here, raised to the power minus n squared over 2n is the size of the matrix. So this is just a number. I multiplied my exponent by a number, and this this number is represented in the form of this Gaussian integral, which is just a constant. The nice thing is that this number actually is 1 as long as you take the replica limit. Maybe. But it's very nice that the limit is 1, so I have even fewer reasons to care.
So the reason because of which we cannot do it with M is just the fact that we integrate not over the M matrix but over the d phi
Yes.
stuff, right? And what is the difference of measure of integration over the matrix Q and over the
Okay,
phi
integration over the matrix Q is very straightforward. You take each matrix element of Q and you integrate over it as an independent variable.
Okay, so you're like, as far as I understand this, so you write out a Gaussian integral for Q
Yeah.
squared, and then you shift it by M.
Yeah, actually I have included M here inside, but the integral does not depend on this M yet because it's just a pure shift.
Yeah, the only problem is like M is Grassmann.
No, M is not Grassmann. M is
It's a pair.
quadratic. It's a pair of Grassmann, so it's a usual matrix. And I have selected all the coefficients here in this shift and here in front in a very specific way. Namely, if you now expand this square, the term with M squared will identically cancel. So this whole thing was designed. This is called Hubbard-Srutonovich transformation. It was designed exactly to kill this M squared term in favor of some other terms. So just rewriting the same thing, even further, I have an integral over the matrix Q. Probably I should do it a bit below. The integral over Q, exponent of just the same thing. I now expand the square, minus pi nu over 4 tau, integral over R, trace of Q squared. This is the first term. And then there is a cross term, well, Q is multiplied with M, which should be minus 1 over 2 tau trace Q times M, right? Just a side note, trace Q times M equals Qij phi j phi dagger I. This is M and this is Q equals minus phi dagger I Qij phi j. Because these phi's, they are Grassmann variables, I can take this phi dagger I and commute it to the first place, and when I go through this phi, I change the sign. So this is what I have written here. Phi dagger Q phi with an opposite sign. So the whole essence of this Hubbard-Srutonovich transformation is the following. We originally had an exponential of the product of 4 fields phi, and we have transformed it to some other expression which is only quadratic in phi, but at the cost of introducing a new variable Q and a new integration And that's it. It's just a Gaussian integral in Q. If you compute this Gaussian integral, you will get back to the original 4 phi term. Any questions?
Okay, so basically the same question, but the measure of integration over d f prime, right? You have this matrix M I J. It seems that it should be exactly the same measure of integration over dq. No?
No. We don't have any integration over M. We have integration over phi and phi star, and we have an integration over matrix Q.
Yes, but I mean, like, as far as integration over df is just integration over each element, each d I.
Yes.
Integration over d prime, each df prime. So they are independent variables, right? And we just combine them into the matrix.
Yeah, it's just a notation. M is a product of two phis. It's not a new variable. We do not integrate over
At
M.
the end of the day, this is still the integration over each element of M,
Yes.
right?
Yes.
And it
Yes.
is exactly the same measure like integration over each
No.
element of Q.
No. Q has n squared elements.
Yes.
It's a matrix. Phis are only 2 times n independent variables. It's not n squared.
Yeah.
So we integrate over original phis. We do not integrate over the matrix M. We integrate over the matrix Q, each element separately, and over two vectors phi and phi dagger.
Thank you.
Does Q have any physical interpretation yet, or?
So far, not no, and later also will be very problematic. But actually it's the main object that Sigma model deals with, so we will discuss it in a lot of details for the rest of this whole course. Still, I'm not sure what simple physical meaning
Like, for example,
can
if
assign
this
to-
were an electron gas, like if this were if V were really an interaction, then it would behave like plasmons, right?
Yeah, then it will be like
But here it's
like
not
electric
really an
potential.
interaction. It's like an interaction that results from.
Yeah, it's an interaction that resulted from averaging. That's why it's not a real interaction potential. It's some, if you like, it's an interaction potential which, for the interaction that does for you disorder average. Okay, so just to summarize this part, we, after doing all this stuff, we now have a new action. New action S now depends on Q, on this matrix Q, and on the fields phi and phi star, and has the following form. Everything that stays in the exponent with a minus sign is the action. This is the first term. Pi nu over 4 tau integral over space trace of Q squared. Then there is another part of the action which is minus I. It's also an integral minus I, right? An integral over space phi dagger, and then everything that we had originally, epsilon minus psi of p, well actually not everything, there is no random potential anymore, minus psi of p plus omega over 2 lambda. Then I will leave some space here and put phi in the end. This is my action. This first term is this one. All these terms are the terms that were inherited from the original action that do not depend on disorder, so they just move here. And then there is this term, the second one, which also has the form phi dagger phi with some matrix in between. So I have minus I and plus 1 over 2 tau here, which means it is plus I q over 2 tau. So this is my new action. It has a field q, which is a matrix, big matrix, which has its own quadratic action, quite simple. And then this field q looks like a potential for my electrons. It's added to the Hamiltonian, well, with an I, but who cares? It's added to the Hamiltonian as a potential would do in the usual interacting problem. So I have electrons that live in the metal. They have some dispersion psi of p, and they feel this potential, which is matrix valued, which is called q, and this potential has its own life, and both the life of this potential and the interaction contain the parameter tau, which appeared due to disorder. So tau is the only thing that we remember about the disorder that is averaged out. Minus I times plus I is plus 1. So it's, I mean, in the exponent you should have minus action in the exponent.
Potential is imaginary, it's the game.
No, potential should be, you mean which potential?
I times q.
Well, I say it looks like a potential, I don't say it is a potential. It's something that interacts with the electron phi. So once again, on a diagrammatic level, originally we had this dashed line here. Let me put it like this. And we had two fields, phi and phi star, phi and phi star. And they even had replica indices. This is I, J, oh, sorry, I, and J here. We have the same random potential in every replica, which means that when we average, we have a correlation between potential acting in replica number I and potential acting in the replica number J. So this dashed line is what is this Fermion term that we had originally. And now, just a moment, and now we have replaced this interaction by saying that this field phi I, this one, and this field phi j star, they interact with some object which is a Q matrix. This is a matrix Q with indices ij. And then we have a separately Q squared. So if we fuse two such objects, we will restore the original dashed line.
So here on so this new action on the left hand you have so Q squared is an n by n matrix, if I understand.
Yes.
Right? But phi is a two-component object.
Well, actually, I was not too accurate. Q has the same size as phi, so it's phi has n replicas inside and also retarded and advanced structure, so Q is 2n by 2n.
So it's a matrix of matrices.
No. It's a matrix of the size 2n. Well, or if you like, yeah, it's in the terms of product of retarded, advanced, and replicas. It's the same size as these vectors. Otherwise, you cannot just multiply them.
Okay, so instead of having phi, we can imagine that phi is now a 2n vector.
Yeah.
With
Phi-
retarded and,
Yeah, phi is a 2n column, phi dagger is a 2n row, Q is a 2n by 2n matrix.
or we,
As you defined in the previous lecture, the big phi consists of small phi's retarded and advanced, so this is the exact.
Yeah, this is the exact notation.
yeah, I was just asking so I don't get confused. I was asking so I don't get confused.
Okay. So, the step number 6, we already have this action. and we have achieved some intermediate goal, we make it quadratic in phi. So we wanted to get rid of this spurious interaction, or something that looks like interaction in phi. We introduced the new field Q. Now our action is again Gaussian quadratic action in the variables phi. So we can do a Gaussian integration. Gaussian integral in the variables phi. Partition function z is an integral over all phi fields, as I explained earlier, of the action. Yeah, this is now our new action. So I should add here the integration over q minus s of q phi and phi star. This is just the partition function we had from the very beginning. It was the phi integral of the exponent of the action. Now this exponent of the action itself was represented as the q integral of the exponent of the new action. And this new action here is quadratic in phi. So I can just explicitly compute this integral and get rid of the phi fields.
Now I just have a problem. So the sign of the interaction term. So if you multiply minus sign, you should get plus 1.
This correct?
But in the above exponent, we have minus.
And we have minus here.
All right, so that's minus.
Okay, so our goal, Gaussian integral in phi, we would like to compute this integral such that we are left with the action which depends only on q and not on phi. So last time I told you a little bit about how to do the Gaussian integral in Grassmann variables. So now we are going to do exactly this. The result of the integration will be dq. This didn't change. Then our action has a part which does not depend on phi, this one. So I will put it here. Exponent of minus pi nu over 4 tau trace of q squared. This thing is integrated over space. Yeah, this is the dq and the part of the exponential here. And what is left times the phi integral over the exponential of this term. Is it so bad? So the Gaussian integral. The Gaussian integral over the fields phi of this exponent is, as we discussed last time, is a determinant of this matrix, this whole matrix here. Epsilon minus psi of p plus omega over 2 lambda plus iq over 2 tau. So we have integral over q, this exponent times this determinant. This is a complicated thing. Yeah, it's an operator, so it's a matrix infinity by infinity. It acts on some functions in real space, but still you can think of it as just a very big matrix, and it has a very big determinant.
So, can you explain why are you calculating the partition function if we are actually at the other object?
Yeah, just because the other object is lengthier. It's the same with some pre-exponential terms, and I don't like to write them every time. That's why I talk about partition function.
Because you should times
You mean this one?
Yeah.
Yes, in principle you should,
But
but in the replica limit it will be again unity. Because it's this I multiplies each row of this matrix, and there are 2n rows in replica space. When n goes to 0, you have I to power 2n, n goes to 0, you have unity.
Also,
sorry,
like
it's not
partitions.
about community.
Times, okay, times, how should I say this? Well, actually, it doesn't matter. I can put I here. That's fine.
Also, I think also like this partition function is defined only up to a multiplicative factor.
Yeah, but the nice thing is that this multiplicative factor is 1.
Well, okay, but even if it weren't one, you don't care.
If it's not 1, I will be a bit worried, but
I mean, like, because as far as I know, like these Hubbard-Stratonovich transformations are done all over the place, not only for replica trace.
yeah, of course, but usually you should, well, at least you should try to trace this constant, whether it's dangerous or not.
I don't know if it's possible. Because technically this is a factor of I at every point in space.
Yeah, actually it's also at every point in space. That's why I don't know how to write it separately.
We used theoretical limits here. Where n goes to 0.
We know that in the very end of the calculation, we will take the replica limit when we compute the green function. That's why whenever we encounter something that is going to be simplified in the replica limit, we sometimes take it not in the very last step, but in some intermediate steps for some intermediate parts, just
So it is
to make our life easier. Actually, you can keep I here, it will not change much. I mean,
I'm not worried about I asked about where you doing this replica limit. That's my question.
when,
Where?
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 In the expression for the green function, which is not here, it was many lines above, there was limit n to 0 of the integral. So all these integrals at some last part of the, I can show you. Yeah, I should scroll this like million lines up. Did I break it? It was here, in the expression for the green function. And this is more or less the same integral with the same action. So I'm now doing transformations to this integral without the pre-exponent because I don't like it. So I do it for z, which is the same integral without pre-exponent. And then, in the very end, when I compute the green function or some other average, I will take the replica limit.
Okay, that is okay.
Yeah,
What is n?
n is the number of replicas. It's an integer number, which can be any integer, but in the very end we will take the limit n to 0, so n does not enter in any final result. It's a trick. I explained it last time how we do this thing. It's just a number that we have introduced, and then we will get rid of it in the end. It has.
So basically, like, if we didn't map this to the new theory of Q, right, then we would basically have an interacting field theory with no tadpoles, because n gets rid of
Yes.
tadpoles, right?
N will get rid of tadpoles, that's correct.
Because you would get a factor of n for each tadpole.
Yep. This is,
Not only that falls, right? Something else as well.
yeah, but tadpoles in particular. Okay, so about this point, I have another useful identity, which is correct for any matrix. The identity is the following. The logarithm of determinant of any matrix equals the trace of the logarithm of the same matrix. Some people even use this identity to define what determinant is. This is a definition of determinant. Yeah, it's just a useful identity. Again, I will not prove it, but I will apply this identity to this determinant that I have here. Namely, I will say that this whole thing is the Q integral of the exponent of a yet new action which now depends only on Q. And this new action S of Q is the first part, this one, is the same, nothing changed, pi nu over 4 tau integral over space trace Q squared. And the second part, so this one, and the second part is the exponent of the logarithm of this determinant. So this determinant equals the exponent of its own logarithm, and its own logarithm equals the trace of the logarithm of the matrix, and so on. So it's minus trace of logarithm of this operator, which is epsilon minus psi of p plus omega over 2 lambda plus iq over 2 tau. This is our new action. It now contains only Q and nothing else. And instead of this, it's almost there, instead of this Gaussian part with phi, we have now a trace of the logarithm of the same operator. And this is actually, now to your question, it was I under the determinant, it will be I under this here, but logarithm of product is the sum of logarithms, so I can say that this is just plus a constant to the whole action, and it's not physically relevant. But it's even nicer that this constant actually is 0 in the replica limit. Okay, so this is the end of our Gaussian integration step. And we are going to step number 7. So we have an action, we can do whatever we like with it. All we did from starting from the very beginning up to this point, everything was the exact transformation. We did not apply any approximations so far. And we arrived at this action, which is an ugly object because it's highly nonlinear. I mean, it's a logarithm of an operator which contains Q inside and which is traced. So it's some enormous thing. I don't know even how to think about it, how to think about such a function of Q. But still, it's our exact action. It's the exact thing. We need to do some approximation to it in order to do at least some computation. And this approximation that we're going to do first is what is called the saddle point approximation. Saddle point approximation. Namely, we are saying the following thing. We have an action. It stays in the exponent. So, for example, in our partition function, we should sum over all possible values of Q of these exponents, this integral. But the main contribution to this integral comes only from configurations of Q which minimize the action. The larger is your action, the larger is this negative number in the exponent, the smaller is the contribution. So mainly the integral over Q comes from those configurations of Q that minimize this action. This is called either semi-classical approximation or mathematical terms it's a saddle point approximation. And of course there should be some parameter which tells us where this approximation works, and actually here there is such a parameter, and it's exactly the same parameter we already discussed earlier, which tells us that tau is a large number compared to Fermi energy.
So now solve the Euler-Lagrange equations for this.
Yeah, exactly. So what we do, we are trying to find where which matrix Q gives the minimum to this action. We try to find the minimum of this action, and in order to find minimum, we just take a derivative and say derivative equals 0. This is where the minimum should be. Yeah.
So looking at the action, I want to say that like nu over tau is a big parameter. Right?
Nu over tau, yeah, but actually it has a dimension, so you should. I mean,
Yes,
it's
Is Q dimensionless?
Q is dimensionless, yes.
Okay, so we multiply it on some character with the integration scale.
yeah, I mean like I somehow want to see like the exact small parameter that we used in the last approximation actually. Just looking at the action, if it is possible.
I will try doing this not here, but a few lines later on. So we take a derivative in Q of this action. Actually, it's not a derivative, it's what is called a variation, because it's a functional. Take a variation, delta S by delta Q, and we want it to be 0. So from the first term, it's very simple. It's pi nu over 2 tau Q. When you take a derivative of Q squared, you get Q. And when you take a derivative of the logarithm, you get the inverse of the argument. So it's minus I over 2 tau, and then this whole operator in the square brackets, epsilon minus psi of p plus omega over 2 lambda plus iq over 2 tau inverse. This is the inverse operator. And actually, since this is an operator, it's an important thing I forgot, of course. I take the derivative of q at a particular point in space. Q is a function of space. So what I get is q at the same point in space here, and there I get this operator taken as a matrix, a diagonal element of this matrix also taken at the same point. Now, just a reminder, we had some interesting equation a few lectures ago, and this interesting equation looked like that. Sigma equals 1 over 2 pi nu tau integral d-dimensional integral over momentum 1 over epsilon minus psi of p minus sigma. Does this look familiar? This is called self-consistent Born approximation. We had this equation when we discussed the averaging of the green function and the self-energy for this averaging calculated in the self-consistent Born approximation. We found that this self-energy is the solution to this equation. Now, if you compare this equation to this equation, it is really extremely similar. Yeah, so it's 0 here. So this part equals that part. 1 over pi nu is already here. 1 over 2 tau is a bit different, but if you do the following thing, if you say that imaginary part of sigma, if you replace it with the matrix Q, it will be the same equation with the matrix Q over 2 tau, with what we have here.
But matrix Q has replicates sigma doesn't.
Yeah, of course. That's why I don't say they're equal. They have the same equation. But one equation is a matrix, of course, the other one is scalar. Yeah, I'm just saying this is an equation which looks very similar to what we had as a self-consistent Born self-consistency equation for this self-energy. And I'm saying this just because we already immediately know one particular solution, because we did solve this equation before. And the solution was that imaginary part of sigma is just 1 over 2 tau. So actually, a very simple solution to this equation, a very simple solution is Q equals 1. Q equals 1 satisfies this equation. Up to some things that I don't want to get into. Actually, Q equals minus 1 also satisfies. Because for the self-consistent Born approximation, we have two solutions, one retarded and one advanced. And this imaginary part of sigma was plus or minus I over 2 tau, which corresponds to Q equals either plus or minus 1. Both numbers do satisfy this equation. So far, we have found two saddle points, Q equals 1 and Q equals minus 1.
Is this like positive and negative identity, or is it plus 1 for
It's a matrix, yeah, it's the identity matrix. I mean,
or is it like plus 1 for the retarded portion and minus 1 for the advanced portion?
very good question. Actually, you can take the matrix Q and put plus and minus 1 in any order on the diagonal, and it still will satisfy the equation. But the correct way of doing this is indeed to say that Q is plus 1 for retarded portion and minus 1 for the advanced portion, which has a special name. It's called lambda. But the reason why this is the correct choice of the solution is not so easy. Actually, I have removed this, but originally we had plus I0 lambda here. So the intuition is like this. The Q matrix replaces this I0, and it would be better if it will not change the sign of the imaginary part, because it will violate some causality properties of these green functions. So we want our retarded green function to remain retarded and our advanced function to remain advanced. That's why in SCBA we took the solution for sigma, which has the same sign. I0 becomes I over 2 tau, minus I0 becomes minus I over 2 tau. And for the same reason, with a Q, we take a diagonal matrix which has the same sign as it was originally with I0. So this is the correct thing. Q equals lambda is a solution to the saddle point approximation. And the action, this whole action, is minimized when Q equals lambda. Very nice. This is a very important thing. I should write it here in some special color. Red, yeah, red. Is it red? No.
Your finger is
Q equals lambda minimizes the action, minimizes S of Q. This red is not so bright, I believe. it minimizes S of Q, and it has all the correct signs in order to maintain the
Yeah, I mean,
causality.
the question was exactly about the causality. As far as we just say that the green function is just a solution to, we define the green function as just as inverse to the operator, right? So in principle, it doesn't care about the causality.
No.
So-
This was in the very beginning of the very first lecture. You cannot invert an operator if this operator has zero eigenvalue. So to get rid of zero eigenvalues, we have shifted energy to either plus I0 or minus I0. And we get two different green functions with two different analytic properties. One is retarded.
Yeah.
It is analytic in the upper half plane, and it is zero at negative times. The other one is advanced. It is analytic in the lower half plane, and it is zero at positive times. And we want to keep these properties here even in the presence of disorder.
Okay, I'll work this later. Yeah.
So if for some reason you take the retarded sector and you say Q equals -1, you will, by mistake, make a retarded object behaving as advanced one.
Yeah. Okay, yes. That's for sure, but so far there would be no problems. Right? Formally we can do it.
Formally you can, yeah.
Okay.
Well, actually, look, you cannot. I'm sorry. You cannot, but the reason is a bit harder to explain. So you should go back to the Hubbard-Stoyanovich
Yes.
transformation to see why you cannot. The problem is that when I take this integral over Q, this Gaussian integral over Q to decouple the fields, I had Q minus M in the square.
Yes.
I did a shift of the Q variable by the variable M.
Okay.
So actually when I say take the saddle point, it means in the Q integral, in this action with Q, we shift the contour of the integration in Q. So this saddle point is not a real number, it has some imaginary thing. And also this operator here has a singular point when this logarithm is singular when the operator has zero eigenvalue. So you cannot shift the contour such that it crosses the real axis. You can shift it only in that half plane where you were originally.
Okay. So because we need to shift the contour when we do Hubbard-Stoyanovich.
When you sorry. When you do saddle point approximation, you shift the contour such that it passes through the saddle point. So you should choose the saddle point in the same half plane, because you cannot shift it in the other half plane because you have some singularities on the real axis.
And that's why Q preserves the same
Yes.
symmetry as far as M.
This is the reason why this Q equals to lambda is the only saddle point where you can actually shift the contour.
Yeah, okay.
Sorry, it was misleading. It has nothing to do with Hubbard-Stoyanovich. It just has.
Yes, just when we take integral over phi.
We already took it, so forgot about Hubbard-Stoyanovich.
Yes.
We just do saddle point approximation. We have some object, and we say, I would like to find the minimum of my action, but not only because I like it to be minimized, I want my integral over Q. Oops, wrong with this. I want my integral over Q, this integral here, this integral with the action. I would like to pass the to have my integration control going through the saddle point.
Yes.
And I have many saddle points, but
That's why we
I
have to
cannot
say
reach
that.
all of them by. Yeah, so actually we had here also plus I0 lambda. Q replace this thing. So if Q has the same sign as lambda, we will not cross the zero of this operator.
Thank you.
So Q equals lambda is a very nice point which is reachable, which is the minimum of the action, and everything is fine. But it turns out that it's not the only minimum of the action. There are other values of Q which provide the same value for the action, which is, I mean, this minimum is degenerate. It's not a single point, it's actually some larger object. And to see this, we can, this is something, yeah. To see this, we can go a few steps back to the action which still contains the phi fields. Just to remind you, we had originally the action which contained both q and phi. This action has pi nu, I just repeat, we already had this equation before, has trace of q squared. And it has phi dagger with the same operator here. Plus iq over 2 tau. So this is the result of Hubbard's Topology transformation before we took the Gaussian integral. It was this action. And it depends both on q and phi. And we did Gaussian integration. We integrated out the phi fields. So let's do the following thing. Before integrating out phi fields, we will do a change of variable. We will say phi field is good, but let's do some linear transformation of these fields before integrating it. T is a matrix. We take our field phi and we say replace phi with t times phi. It's just a change of variable in the integral. And also we say take the field phi dagger and replace it with phi dagger times t dagger. And actually this matrix T must be a unitary matrix. Just so T dagger times T should be unity. I just selected my matrix T to be unitary. I can put any matrix there. I like it to be unitary because I want this epsilon term to be preserved. So I do this change of variables and my action remains almost the same. The first term doesn't know anything about phi, and this term becomes phi dagger epsilon minus t dagger psi t plus omega over 2 t dagger lambda t plus I over 2 tau t dagger q t phi. Right? This is what happened. So since I have chosen t dagger t to be 1, this epsilon thing remains epsilon. It's just a unity there. There is no matrix. This psi actually is also, it acts in the real space. So if I say t equals constant, t does not change in real space, then this term will be just psi. Nothing special. Then if I also assume omega equals 0, this term will disappear. And the only place where this matrix T actually appears, it multiplies the Q matrix.
Oh, wait. So omega is 0 is... If omega is 0, then it's the
It's an assumption, yeah. So if omega is 0, if I took a constant matrix T, I can also remove it from here. Yeah, if omega is 0, I didn't have this term from the very beginning.
Yeah.
So this is the only thing that happens. Q is Q, so if I do this transformation, it's the same as saying that the matrix Q is changed into T dagger Q T, or since T is unitary, T dagger is the same as the T inverse. I prefer making it inverse. And then if I do this substitution, the trace of Q squared will not change.
Well, technically, the action is invariant even if T weren't unitary, but then the measure isn't, right? So.
No, I want epsilon to become.
I mean, epsilon will still be fixed because from the left you would just multiply an inverse with the equation.
Right.
The reason, well, I would guess that the reason why it's unitary is because you don't want the measure, or like in the partition function, you don't want the measure to change, because then you get additional factors from it.
Look, the problem is that even in that case, I will not get an additional factors in front. The problem why I would like it to be unitary is that well, actually, there's no any strict reason. I just selected it this way.
Yeah, I guess that like if we are searching for all the values at which are degenerate, right? Then in principle the action is no different if we weren't unitary.
Okay, look. Now I answered your question. I wanted to avoid this topic from the very beginning, but in the Hubbard-Certonowitz transformation, which I never mentioned, there is a restriction on the matrix Q, such that the integral over Q converges. And this restriction is very simple. Q should be a Hermitian matrix. Then I need this to preserve its hermiticity. Just an example. Imagine you have an integral, the Gaussian integral, exponent of minus x squared. It's a known thing. It's a Poisson integral. It equals to square root of pi. But only if x is a real number. Because if x is an imaginary number, it diverges. So this condition x is real in matrix language translates into matrix is Hermitian.
Yeah, okay. Yeah, that makes sense. Okay.
Why do we need the T, the constant in space? It looks enough that T is
I want t to be constant in space.
diagonal in momentum representation, so it will commute with its psi.
Diagonal in momentum representation, but different at different momenta. Look, t should be a function of point. It should be diagonal in real space representation because q is a function of a single point. So when you multiply with t, you should not get an operator, but still a function of point. T should be a function of a single point. That's why to compute with xi of p, it should be constant in space.
Yeah, I think you will want to slowly laying in time at some later point.
Yeah, of course.
Sorry, it's not in time, it's space.
In space, yeah. Maybe even today. So what I'm trying to say that as long as we know that lambda is the correct lambda, is a good, correct saddle point of our action, the same is true if we take lambda and multiply it with any matrix, any unitary matrix T and T inverse from the two sides. This T is, I will write it explicitly, is a unitary matrix of the size 2n. For any unitary matrix of the size 2n, this value of Q is a saddle point. So we have not a single point, we have a whole space of these points which is parametrized by a unitary matrix. And this is extremely important identity. Moreover, these are all physically relevant saddle points that the action has. They're all contained here, and just for somebody who was worried about it, we can apply a unitary transformation which interchanges plus and minus 1. So even the solution which is -1 in retarded part and +1 is advanced is a good one actually. We just start from lambda because about lambda we know for sure that this is a nice point, and then we apply any rotations and we see this whole thing. So we have not a saddle point, we have this thing which is called the saddle manifold. Saddle manifold. The Q matrix. So we will now do what is called semi-classical approximation or saddle point approximation. This approximation means that we say we do not take into account all possible matrices Q. We will limit our matrices Q to be matrices of this structure. We want to take into account only contributions from Q that have this form. Then somebody will ask me, hopefully, what's the point of taking all this Q matrices? We know the action is minimized already, and it's the same for any Q. For all values of Q like this, the action is the same. So it's like, you have some potential, it has a minimum, but this minimum is not a single point. It's like a trench which has some extent. And so trench is usually a line. This one is more than a line, but still. We want to limit our consideration only to these Q matrices, but also we will now restore what Dima just mentioned. We will lift these conditions that T should be constant and omega should be 0. So when T is constant, Q is the same everywhere in space, and omega is 0, then for all such matrices we have exactly the same action, which is some minimum possible number. Now if we allow T to change in space, it's not a constant, and if we allow omega to be non-zero, to be some small number, I just remind you we did it already with diagrams that Q and omega are small parameters. We're small parameters when we studied diffusion. So omega is a small parameter, and Q, the momentum, is how our diffusion changes in space, how fast. It also slowly changes in space. So if we lift these two restrictions, our action will not be a constant anymore. It will be some function of Q. So it looks like this. You have how to picture it. You have a potential landscape, then you have a trench which is very deep, and once you got inside you cannot get out. You can only walk along this trench, but then there is some landscape, some small changing of the height inside this trench. So we want our Q matrix to live inside, but still the action will not be a constant. It will be some meaningful function of Q.
So what is this, like some weird space-time with motion with multiple times and multiple space dimensions?
Multiple space, there is no time here. It's all multi-dimensional
Like
space.
for example, one sign and then the other sign for lambda would be like how we would distinguish one another type of space.
Actually, I don't get your analogy.
Like in space-time, lambda would be chosen like -1, 1, 1, 1.
In space-time, you mean you have a metric which is like this Minkowski metric. But no, actually, this is a different thing.
Well, it's a different, but instead of like, for example, if n is 2 or if n is 1, if n is 1, this is like literally a space-time. Okay.
If n is 1,
Yeah.
Okay, it might happen that yes, you have some relativistic theory with the similar fields, but in our case, n is any number. N is 0 in the very end. Yeah? So just be careful. Okay, so this was step number 7 last time. So we will have step number 8, and this will be the final step. Step number 8 is called gradient expansion. gradient expansion or expansion. So we now say that t of r is a slowly changing function in space. It changes slowly. Slowly changing. And also we say that omega is not 0, but small, which means that omega tau is much smaller than 1. And we will extract from this logarithm, which was somewhere on top of this, we will expand our action in small gradients of t and in small omega. This is called gradient expansion. So let me write the action once again. Action of q. Well, first of all, the first term of the action, pi nu over 4 tau trace q squared, I just discard it completely. Because for this matrix q, it's just a number. It does not depend on t. It's a trace of lambda squared. In the replica limit it's 0. So there are many reasons to just discard it. And what remains is, I forgot, is it minus trace? It's plus trace logarithm of this operator here, epsilon minus psi plus omega over 2 lambda plus I over 2 tau t inverse lambda t. This is my action. This thing here is called Q. It's just my representation of the Q matrix. And I now assume that omega is small but non-zero, and also these t's, they are some slow functions in space. So what can I do with this action? I can do the same trick I did before. I will multiply this whole operator here with t inverse from the right and with t from the left. Yeah, it's a logarithm of determinant. You can multiply determinant by something. You can conjugate it with some matrix. The determinant doesn't change. Or under trace, you can say that this t can be moved there and cancels that t. So why do I do this? I do this because I would like to isolate something which does not contain these t matrices. I will have now trace logarithm of epsilon minus t psi t inverse plus omega over 2 t lambda t inverse plus I over 2 tau lambda. Nothing changed so far. So this thing is small. Omega is small. This is some small object. This object is a bit trickier, but it can be also transformed. So if I can commute psi and t, then t cancels. So this object, t psi t inverse, approximately equals, exactly equals psi plus a commutator of t and psi times t inverse. Oops, this is something I did not want. This is exact. And now this commutator is small. If t changes slowly in space, it almost commutes with psi. The commutator is small, which means, and actually now approximately equal psi, and this commutator is, who can tell me? It's I V Fermi gradient of t times t inverse.
Alright, you wanna, okay. Specifically for quadratic.
No, for any. V Fermi is the true Fermi velocity on the true Fermi surface.
Why was I?
Because momentum is I times nabla. So actually what I did, I said that psi is like V Fermi times momentum,
Yeah, okay.
and then I commuted t with this momentum. It gave me, and momentum is minus I gradient, so it's like minus I V Fermi nabla. But since psi stands here, the commutator gives plus I. So once again, the same action is now written like this. I have trace logarithm. First I collect all terms that are not small. Epsilon minus psi that comes from here, and plus I lambda over 2 tau. And then I have plus some small terms, and these small terms are minus I V Fermi nabla t inverse. This is one. And this is the second one, plus omega over 2 t lambda t inverse. And I will introduce special notations for these things. First, this part in front is very simple. It's a diagonal matrix. Lambda is plus minus 1. This matrix has a name. It's called the inverse green function, which explicitly is the inverse retarded function here and the inverse advanced function here. Already average over disorder, so with 1 over 2 tau. And this is a diagonal matrix. On the diagonal it has epsilon minus psi plus or minus I over 2 tau. Something happened to my notes. Yeah, it's better. Then this part here is some small addition. Gradient of t is small. I will just call it A, and this thing I will call it B, just to make it shorter. So,
This then has a nice form in momentum space, right?
yeah. Well, actually, this thing is diagonal in momentum space, this first one. But those are not, those are written in real space.
Yeah, but in momentum space they're also diagonal. Or at least nice. It's like the gradient of t.
No, it's not. It's a function of R. It's a function of
Well, yeah,
point.
t is a function of r, but like.
And gradient of t is another function of R.
Well, no, gradient is just multiplying by t.
Wait.
By t.
So it's even worse.
If you have a function of R, then you take a gradient, you get another real function of R.
Sure. But you can still write it as a function.
You
of
take
p
several
times-
non-trivial functions.
You can just write it as a function of p times p.
But it's not supposed to be a function of P.
But if it's a function of r, you can get a function of p out of it.
If it's an operator, then not.
Well, you can just perform a Fourier.
Yeah, but you will have a matrix. I mean, it will be a function of two momenta, not a single one.
You will function of difference P1 minus P2. If you have an operator that is local with R, then it's not local with P and vice versa.
An operator is diagonal in R, means it depends on a single R, but it's not diagonal in P, means it depends on two indices, not on one.
That's true. Okay.
Okay, so, but it depends only on the difference, P1 minus P2. Okay, so we have our action. This is our main part, and these are small corrections, and we will expand the logarithm in the power series.
So you can, as far as
they have no,
How can switch?
we cannot.
We cannot.
It's the same story as we did with the diffusion when we expanded to the second order in Q, but only to the first order in omega.
Why we should keep join with greater than t? Why? Why we should keep a to join?
Well, just because it's not zero,
But it's small.
yeah. If you throw away, you will get a theory that is very, how to say, boring. It's just your action will be just a number, not dependent on anything in this world.
You want to get an effective equation on your manifold where Q has a fixed eigenvalue.
Look, we are saying T is not a constant, it slowly changes in space. And we would like to see what is the effect of this. Now you tell me, please neglect the gradient because it's small. Then we are back to the situation when T is a constant in space.
I didn't say you neglect this, I asked why you don't know.
Because I want to take into account variations of T and see what they produce.
Okay, we should answer my question. Okay.
But I think the answer is that in your calculation, A will be of about the same order as B. So that's why you want to keep both A and B just to the first order.
Well, the problem is that I want B to the first order and A to the second order. That's why I hesitate to give this answer. Well, actually, it has Fermi velocity, which is relatively large, but it's a vector object which averages to something small. Well, you know this drill better than me, so. Okay, one last thing. I will just use these letters G, A, and B and write this thing, trace log of G inverse. This is the zero order term when I neglected A and B. And then I will take this G inverse out and write here 1 plus G times A and plus G times B. This is just a rewriting of the same thing here. Yeah? If G inverse is taken inside, it's G inverse plus A plus B. But then, since I have a product under the logarithm, I can write a sum of two logarithms. It's a logarithm of G inverse plus a logarithm of 1 plus GA plus GB. And finally, first of all, I will disregard this thing. It's a constant. It does not depend on T. It has only these numbers here. It's just a number. I don't need it in my action. And that last logarithm, I will expand in small a and small b, and it will give me a trace of let's start with B. Trace of G times B plus G times A minus GA squared divided by 2. So I expand to the linear order in B and up to the quadratic order in A. And the reason I'm doing this is because this linear order in A will be 0. So I need the next order. And we already did this a few times before. When we calculated the diffusion ladder, we did this expansion in Q up to the second order and in omega up to the linear order. So, what's this first term? G times B. It's very simple. It's a trace of G is just this diagonal matrix GR, GA, and B is this matrix. So it's omega over 2 I write B first and G next times G, this matrix G, taken at coincident points. Yeah, it's a trace, it's also a trace in real space. G is an operator, but A and B are local functions. They depend only on a single point. So it's like a diagram. You have G, which goes and comes back to the same point, and you have the operator B sitting at that point. This is a trace of G times B. G should be taken at the same point where T is taken. So it's T of R, T inverse of R, and G taken twice at the same point R. So actually, there are many ways how to do this, how to compute G at coincident points, but I should remind you we already had this object today in the saddle point equation, which was the same as the self-consistent Born approximation, which was many times the same. It contains the green function at coincident points equals to something. Let's see, if I scroll this for long enough time, I will reach the equation. Here it is. Yeah. Green function at coincident points, is this green function without omega, is equal to minus I pi nu q. And q is lambda in this approximation. Minus I pi nu. This is there any faster way to do this? So what I'm trying to say is that this G here equals minus I pi nu lambda.
From which term does this come? This comes from
This one. G times B.
Oh yeah, this is just the first one. Okay.
Yeah, and then the second term is actually 0 because it contains this A contains Fermi velocity inside, and averaging over directions of Fermi velocity gives 0. So I need yet the next term. Why nobody corrected me when I do the expansion of logarithm wrong? Because I did it correctly. Good point. Yeah, for some reason in my notes the sign is opposite. Yes, the sign is wrong. The sign was wrong. This sign is minus already here. Oops. Determinant is the exponent of the trace of the logarithm, but action stays with a minus in the exponent, so it should be minus logarithm. Minus. It should be minus. It should be minus. And it should be minus here. And it should be minus here. So I will write just this last term because the second one is 0. The last term will be plus 1/2. Plus 1/2. And then this GA squared. Oh, that's a tough thing. It's a trace of G times V Fermi gradient of T inverse times G times V Fermi gradient of T inverse. And these objects here, they are taken at some point R. These are at point R prime. And the green functions is between R and R prime, and this green functions is between R prime and R. And Fermi velocity, I don't know at which point. But this thing looks like a diagram. It looks like this diagram.
After integrating over space, you get rid of the Fermi velocity direction, right?
Yeah, I will average over directions. Actually, the point is like this. Look, that's important. T changes slowly in space, and G decays fast at the scale of the mean free path because it contains tau inside. So actually, I can assume that these T's are taken at the same point, and then I integrate the product of two G's just in momentum representation. I can say that these two parts are constants. They do not change between points r and r prime. And I can take them out of the integral, and I will have an integral over r minus r prime, which involves only green functions.
But yeah, but still, like after here, you still have to integrate. After you do all the calculations, you still have to average over directions.
Yes, definitely.
Okay, but you can still probably make it similar in momentum space.
Yeah.
Right.
As soon as I take out these gradients of t out, then the rest is computed in momentum representation.
Okay.
So let's get done with this.
Explain more precisely why for first term we have in function in point RR, depends on RR, but for second point we have R prime just R.
Because the B object is a function of a single point. So it's a diagram like this. B lives in a single point in space, and the green function under the trace should go from this point back to the same point. And here we have two objects. A is another object which lives in a single point in space, but we have two of them, so generally they live at two different points, r and r prime. And then we have the green function that goes from here to there, and the other one back to complete the trace.
Your trace is
Okay,
just.
so if you, is there another way to explain it?
Yes, I can write it explicitly like this. I have a trace of GA. They are big matrices. R is like an index for rows and columns. So it's an integral over dr prime g of r prime times a of r prime times g of r prime r times a of r. This is how you define the trace. You multiply the matrices and you connect the last index of one matrix with the first index of the next matrix, and so on. And the last index of the last matrix should be the same as the first index of the first matrix. And this is exactly what is written here. Just the only point is that A is a diagonal matrix. It has both indices equal to each other, and it's written only once. And the same actually was here. You have trace G times B. B has only one point. That's why G should be taken twice with the same point. What I do next, which is the answer to the other question, I say that A slowly changes in space, and G decays very fast as soon as this difference r minus r prime is larger than A. So this thing approximately is an integral over r, and I take this A of r out. I say that A of r and A of r prime is the same because they did not change. And then I have another integral which involves only two green functions, and this other integral I will write in momentum representation. The problem is that I can, of course, separate them like this, but they should be multiplied like matrices, GA still. So I have to contract matrix indices. I don't want to really to go into this. Let's do the calculation. You will see it right now. It's very easy. So the first term minus I pi nu over 2, I pi nu omega over 2. Trace, I have T lambda T inverse, T lambda T inverse lambda from here. This is the first term. Hopefully with the correct sign. Actually, it's wrong again.
Why do you have either?
I took it from here. But I don't know where I did the mistake, but it should be minus I. Ah, no, it's plus I. No, that's correct. That's correct. Sorry. And another way to write this is I pi nu omega over 2. T inverse lambda T is my Q matrix, so it's just lambda times Q. And this other term, it's trickier. That's why we will write it explicitly in the following way. How to do this? How to do this? How to do this? What's the best way to do this? One. Okay, I will try. I'm not sure if I can do it completely. So it's 1/2. Trace is an integral over all momenta, which is d-dimensional. Then another trace. Then I have retarded function, advanced function, 0, 0, times a gradient of t inverse, and this whole thing is squared. As promised, I assume that gradient of t inverse is like a constant. It does not change much in space. So I just neglected its dependence on r. The whole dependence is only in the green function, which is converted to the momentum space. So I can then restore this r dependence after I integrate out the green functions. And for some reason, yeah, it should be also V Fermi, yeah, A contained V Fermi squared, which gives me V Fermi squared divided by D.
But when you decouple, you shouldn't duplicate everything, and you shouldn't duplicate the retarded advanced tables. You should only keep them.
Yeah, that's why it's a trace of square, and not square of trace.
You use a T slow function.
Yeah, and G is very much localized in space. Yeah, then I'm not sure how to explain this, but I can tell you what the result is. So as usual, we do the integration over xi, and we write these green functions as poles, and then we take residues at these poles. The problem is that we have two of them here, so I should write explicitly this matrix, multiply all of them and take residue each matrix element and then collect it back to a single trace.
Retarded, right? Only.
No, it will be retarded advanced only. Good point. Oh, this is a mouse.
Yeah.
I thought it's something you can erase things, you know. This is a good point. Thank you, Dima. We now know how to solve this. V Fermi squared over 2D, integral, new integral over xi, and then trace of GR 0, 0, 0 gradient T inverse times 0, 0, 0 GK and another gradient T inverse. if you take, we have two green functions inside. If you take two retarded green functions, the integral is 0 because they have poles in the same half plane, and you can complete the contour in the other half plane, and it's 0. If you take twice advanced, it's also 0. So from this square, you necessarily should take one retarded and one advanced function to get a non-zero result.
Maybe.
So I take retarded from the first matrix and advanced from the second. And another option is to take them advanced from the first and retarded from the second, but then I can interchange them under trace, so it's the same thing. I just erase 2, and that's the correct result. Oh, but this is still a lot of writing. So, new V Fermi squared divided by D. This matrix here is just GR times 1 plus lambda over 2. And this matrix here is just GA times 1 minus lambda over 2. I don't need this bracket. GA. So what I have is trace 1/4 1 plus lambda gradient t inverse 1 minus lambda gradient t inverse, and then an integral which involves just the product of GR and GA, which is d psi divided by epsilon minus psi squared plus 1 over 4 tau squared, which equals, I mean the integral is 2 pi tau. I really hope the answer will be correct, because I don't know how to find mistakes. So 1/4 2 pi tau.
Sorry.
Yeah.
Maybe from this equation you can say that this, why you keep only retarded and advanced?
Because if you take, there is also a part with two retarded functions, but in this integral it will have both poles for retarded function in the lower half plane, and the integral will be 0. The integral over psi. Here I have poles up and down, so it's square plus square. Otherwise it will be twice the same half plane, so it will be 0. So what I have here is 1/4 2 pi nu tau pi tau over 2 it's nu diffusion constant pi over 2 times trace of gradient t inverse squared minus lambda gradient t inverse squared. And somewhere far along the way, I have lost the correct sign of this expression. It was minus, sorry, it was minus and another minus. Strange. So my notes say that everything is correct up to overall sign. Look, there is a simple solution to the whole problem.
Maybe it's from two i's from the Green's functions?
No.
But which side do you want?
Maybe it's for homework.
That's a good point, yeah, to do at home. Yeah, let me just check. So it should have been minus already here, and
Yeah, that's from the squares, right? From the expansion.
it's because I squared is minus 1.
Yeah.
So it's when we have this Fermi velocity squared, it is minus here, because it was I v Fermi. Great. Nice thing we didn't do any other mistakes.
Or an even number of them.
Or an even number, exactly. So, homework. Prove the following identity. This thing written here equals pi mu d over 4 trace of gradient q squared. It's an easy one. I even have a hint. To prove this identity, you should start with the answer and try to derive the... Start from here and derive this one.
So now we, okay.
So that's all for today. I'm sorry for a bit mess in the end. Next time we will start from this point and we will do it again in the proper way. Thank you.